All right, good afternoon, everyone. My name is Charles Nebeze, and I'm joined here with my colleague, Lenisa Modley, and we're going to be speaking to you today about 4D data integration for mining. We're hosting John Magagi from Mira Geoscience. This is one of the MICA approved projects, and what we're going to be doing over the next half an hour or so is having a conversation with John about his technology. But before we jump into John's presentation, I want to let you know that there are 16 approved projects under MICA for this funding round. And I'm going to put them on the list here on the screen so you can see those technologies. And we are doing a webinar for each and every one of these funded projects. We'd also like to let you know that our second call for proposals is open right now. So if you'd like to submit a proposal, please just point to the screen here and you'll be able to actually see the call for proposal process. And so you can participate in all that. All right, now it gives me great pleasure to hand over the floor to John Magagi from Mira Geoscience, who's going to speak to us about 4D data integration for mining. John, please go ahead.
All right, thank you very much, Charles. I'll share my screen. And I'll start my PowerPoint here. Screen, just a second. I have to share a different screen, just a moment.
Okay, we got you.
All right, can you see my title slide?
No, not yet, not yet. Oh, there we go. Yes, we see it now. Please go ahead.
Okay, thank you very much again, Charles. So 4D data integration for mining is what I'm speaking about today. By 4D, I mean X, Y, Z, and time. So spatial and temporal data integration. And what we're looking at by data integration is integrating data from any aspect of the mine system, from exploration and the geological model through to the mine operation and production, to the mill, and eventually to tailings and reclamation, to get all of that data, all of those objects in 3 and 4D into one container or data warehouse, where we can do some interesting things with them. For one thing, we can just access them all in one place at one time, but more importantly, we can do some real quantitative work with them. So I'm really pleased that the project has been accepted, and we're now underway with MICA, and we've worked with SEMI before on previous projects. And we've really enjoyed it. The projects have been successful. And in many ways, this project here is an evolution from previous projects that we've undertaken through SEMI. So a little bit about the company, Mira Geoscience. We're headquartered in Montreal. That's where I'm talking from today. We have offices as well in Vancouver and Brisbane and Perth in Australia. We do specialize in data integration. Data integration is really the core of what the company does. And we do that in both 3D and 4D. And we do it from a modeling perspective. We do it from a quantitative integration perspective, visualization, and importantly, analytics. So you can actually gain some insights from all of that data. We have 3 software platforms, which are shown on the right. The one on top is Geoscience Analyst, which is first and foremost a 3D visualization system that enables communication, collaboration, and allows you to build analytical tools on top of it. To the left, below it, is Geoscience Integrator, the data management system. That is the real 4D data management system that's at the core of this project. And then we also work with a powerful tool for 3D Earth modeling, which is very much a part of what we do. So what we're most known for as a company are listed by the bullet points at the left there, geological modeling, mostly for mineral exploration, but we also work in resource modeling and geotechnical hazard, integrated data management and analytics from a mining and geological modeling perspective. So I want to talk first about Geoscience Integrator. That's the data management system that I showed on the previous slide. And this is a system that had its inception in a project that was funded by SEMI back in 2014, 2015. And the origin of the project was that three companies, Glencore, Vale, and Rio Tinto, wanted to have a system where they could combine different kinds of underground mining data into a single data warehouse where users could easily access it. This was initially driven by the Summit research project that was managed by SEMI. And they had three case study mines. So Nickel Rim South, Coleman from Vale, and North Parkes mine, which was a Rio Tinto mine at the time in Australia. And what we were able to develop over a couple of years in that project using those three case study sites was exactly what's shown in this slide. So this particular slide, this image, was from the request for proposal that the three mining companies through SEMI had originally issued. And this is exactly what we delivered and what is commercially available today and has been deployed at several sites today. So it's exactly what's pictured here. You have data coming in from the mine, all different sorts of data from geology to mine engineering, production. As it says, you can see seismic data, extensometer, other kinds of ground deformation, drill holes, geology, blasting, fixed plant activity, mobile equipment tracking, etc. So that's all handled within the system. Importantly, we're able to automatically connect to data sources on site, so you don't require manual upload of the data. The data can be automatically imported into the system, can be conditioned by the system, so the data is all in standard formats. And from there, users can access any of the data. They can query it by space or time or type or keywords or however they want to access it, and they can visualize it. They can visualize it together, they can download it, and then most importantly, they can do something with it. I'll show you a couple of screen images, just what that looks like in the 3D visualizer. So this is Geoscience Analyst, which I mentioned in the first slide as the communication and collaboration platform. So here it is connected to Geoscience Integrator, the data warehouse. What's shown on the screen here is an exploration application looking at just geological structures in the visualization window. And you have an object tree on the left that's really a direct view into the data management system. So the data is not hosted on the user's workstation. It's hosted in the central server, which can either be on premise or more likely these days to be cloud hosted. And then you can easily query whatever data objects you like. In the geological or exploration application, one of the key original use cases was just simply users wanted to be able to draw a box in 3D and say, what data do I have in here? And that's particularly important when you've got a lot of data sets when you're around a mine and where there's been a lot of history. People easily lose track of what data they have and just wanted an easy way to find it. So finding the data, organizing and finding the data is the first thing you need to do. And that's what the original system did. But then more importantly, as I'll talk about in a moment, you also want to be able to do something with that data once you've got it all in one place. This slide here shows a picture of an underground mine. This is actually the old Craig mine in Sudbury. And you can see the mine infrastructure in gray and those balls or spheres floating in space or microseismic events within a certain window. And again, this is just looking into the Geoscience Integrator data warehouse, and it's presenting a table of data at the bottom center and right, you've got panels for accessing different types of data and bringing data into the system. So what can you do with data in a system like this once you've been able to combine geology, mine infrastructure, production, stress data, blasting data, support data? The overall data flow is shown in the schematic. So here we have a list on the left of different types of spatial data. So these are examples of mine data and exploration data that can all easily come into the system. So that arrow in the center just shows the data coming in to Geoscience Integrator, the consolidated 4D data warehouse. You can have non-spatial data come in as well, documents, other kinds of unstructured files, that can all be linked within the system. So that's great. You can easily access the data from there. You can do it through the web interface or through Geoscience Analyst. But you can also start processing the data. There's a Python API, so you can directly hook up machine learning or AI algorithms to the system, which is how it's now often used. And you can automatically generate outputs from that data fusion and artificial intelligence. So data fusion is a term that we often use with this technology, and it really goes to the core of what's innovative about this system. And by data fusion, what we mean is being able to take data of different types. So for example, support, mine production, geology, geotechnical data like ground deformation, and being able to combine it all and do that quantitatively to create some output of value. And the way that's done is we co-locate data in space and time on different points of the mine. So this is what we call a data fusion table. And this is a data fusion table that's being created directly within Geoscience Integrator, which is directly within the system. And this table combines data of many different types and then compares it to something of interest. So the thing of interest in this application is geotechnical hazard. For example, a ground fall or a rock burst, or if it's an open pit mine, it could be a pit slope failure. And what we have is the rows of this table are the individual observations, and those observations are all at some 4D point. So an X, Y, Z, T at each observation. And then for that point at that time, we have a number of variables. Those variables, maybe like disking as an example, is a rock mass variable. Fault proximity is a structural variable. Shear over compressional wave energy is a seismic variable. PV torque stress is a stress variable. So you can have as many of these variables as you want. And importantly, these variables are computed directly from the input data sources within the system. And once you have those variables computed, you can start to look for patterns amongst those variables, in particular patterns in how they relate to something of interest from a business perspective, such as geotechnical hazard. So here the red O's mean there was a hazard at that point, X, Y, Z, T, the X's mean wasn't. And with a table like this, you can now apply machine learning or other kinds of predictive analytics tools to understand the patterns amongst those variables and how they can be used to predict the probability of something like a hazard. This slide here is another view of what we mean by data fusion. This is looking at the Geoscience Integrator web interface, and here we're looking at points. So these are the points of co-location on an open pit. So these are individual vertexes of the pit shell. And the key thing here is that each one of those points, we have a number of properties or variables that have been computed. And again, once you have that done, those variables can be assembled in the table like I showed on the previous slide, and you can start to explore relationships amongst those variables and relationships between the variables and some outcome of interest. Here's another example. This is another view through the Geoscience Integrator web interface. This is a particular level in an underground mine, and here you can immediately see what we mean by 4D. So we're looking at points in space at a particular mine level, and up here on the top right, you can see a level has been indicated. This is the level we want to look at. And here on the center right, you can see that we're looking for data at a certain point in time. So this means you actually have a tracking and history of the values of all of these individual variables at these points throughout the mine over time. And at the bottom right here, we're just selecting which point we want to display as a variable. In this case, rock burst hazard, which is what is shown in the center screen. So that again shows you what we mean by data fusion. So it's points in space and time with multiple variables attributed to them, where we can now explore the relationships amongst those variables in space and time, and the relationship between those variables and some outcome of interest like hazard probability. So that's the background. That's what we have created, and that's actually commercially deployed. What we're doing in this project is we're extending it. So we've done a lot of work in mineral exploration and underground mining operations. We want to extend that work to open pit operations, to the mill, and beyond the mill to environmental and tailings problems. So that means extending the types of data that we can house within the Geoscience Integrator 4D data warehouse, and also starting to explore some of the other business outcomes that we can have an impact on by looking for relationships amongst all of these different variables through space and time. So that's the project in a nutshell. The benefits, all relevant spatial and time-based data are available to users and to other systems that need the data. This is really important. We've been working for years at mine sites, and when you just want data of different types, especially if you're crossing between the geology department and the engineering department, and then I'm sure it's the same when you move on to the mill, the data is in different systems. It's not that the data is not there. The data is there, but it's hard to get your hands on. Some of that data is trapped in filing cabinets, or it's in Excel spreadsheets, it's in AutoCAD, it's in geological modeling platforms. It's just in multiple systems and multiple silos. So with this technology, key benefit is you get all of that data immediately available to all the users and the systems for immediate download to do something with, but also for the system itself to do something with. Reduce manual data handling and costs, particularly the costs of mistakes and the costs implied in trying to just find data. So much data is trapped in Excel spreadsheets on mines. This is a way to get that data into one space where you can do something with it. Improve safety, discovery, productivity, recovery. We've certainly demonstrated improving safety and discovery through the work we've done over the years. We want to extend that into productivity, recovery, and other business outcomes, such as reducing dilution, improving energy consumption, and looking at environmental tailings risks through this project. Why it's innovative. I know there are lots of data management systems around, and there's lots of data management systems on mines. Well, what's special about this one? First of all, when we go to mines today or exploration offices today, most of the data is still on network file systems. It's in Excel sheets, it's in project files, binary project files that are connected to proprietary software systems. This gets that data from the network file system into a structured system where everybody can access it. It's natively 4D, which is innovative. It combines data with models and metadata. By data, I mean the raw data, such as drill hole data or ground deformation monitoring data, whatever the raw data is, with models such as geological models, stress models, etc., and the metadata. So you have the links between all of these at your fingertips. Combine spatial and temporal queries so you can find the data by location or by time. quantitatively integrates the geological model with mine operations. Again, what we see is typically a huge gap between the geology department and the engineering or operations department. People have their data and their models, but when you want to use an aspect of one system and combine it with another system to get some business outcome, it's always difficult. What we call rock-centric data fusion operations as described. So we're looking really at points in the rock mass, X, Y, Z, T. We're able to track them through time, including variables on them, such as grade, which may not change, stress, which will change, but also to track it right from its location in the rock mass through to the mining of that if it's within the ore body, and then tracking it out of the mine to the mill. AI, open source enabled, so we can make use of all the fabulous innovations that have come around in machine learning in the last few years. Automated import and reporting, critically important. People don't want to be manually handling all this stuff. And then on-premise or cloud hosted. And just to give you a sense of what that looks like in a schematic, we show here on the top all sorts of different data types automatically being fed into the data warehouse where you can access it easily, look at charts, whatever. But we also have a spatial data modeling engine running on the server. So there's a database server, and there's also what we call a spatial modeling engine, and it's able to compute things like how far is this point from a fault, or whatever variables we need. It's able to compute them in quasi-real time as new data are imported and stored within the system. It's able to connect to machine learning applications, which is what we already do in both exploration and geotechnical hazard. And it's able to automatically create outputs that go right to your phone or to your desktop. Some quick application examples. I've selected a handful of these where the system is already deployed in either mineral exploration or geotechnical hazard applications, just to give you a sense of it. It's at Freeport Grasberg mine in Indonesia for automated block cave mine geohazard. We've just deployed it at Iron Gold's Westwood mine for strain burst hazard. It's deployed at Mosaic's potash mines in Saskatchewan, where they just want to integrate geology and engineering data. BGC Engineering is a geotechnical consulting company that just wants to manage project data. BGE in Germany is a nuclear waste data management organization that needs to integrate geological data with all sorts of monitoring and operations data. It's being used now at Vale Exploration for the Sudbury Basin data management. And it's been used in several academic projects, such as the CMIC Footprints project. What we're looking for from the MICA Network, we're looking for pilot projects. We want to extend the system beyond geotechnical hazard and mineral exploration, where it's been mostly used, into other kinds of predictive analytics, as we call it, from the mine system. So when you want to predict some business outcome of importance, beyond geotechnical hazard, where we've been mostly working, we think we can, we know we can use the system to give you that. So whether that's blast performance, support performance, looking at grade or dilution, looking at issues around the mine mill reconciliation, looking at geometallurgy, tracking again, metallurgy or mill type variables from the rock mass into the mill. Looking at other types of hazard, and we've been looking at so far, most of our work's been underground. We'd like to extend that to more open pit settings. And then also looking at tailings infrastructure monitoring, where we think we've got a real contribution to make. Yeah, and that's it. If you want to contact me, it's you can get to me through info@mirageoscience.com, or if you contact the MICA Network info, I'm sure they'll get you in touch with me as well. So thank you very much, Charles.
Awesome.
That's all I got.
Thank you very much, John. Really appreciate your presentation. John, we do have a couple of questions for you. But you know what? I'm so happy to see that you've extended your model to look at things like, tailings and some of the issues around tailings. But I want to ask a very specific question about tailings. Is your application going to allow companies to better predict the stability of tailing dam walls? Is that sort of what you're looking at? Maybe you can just clarify what exactly it is that you can do for somebody who's got a tailings dam and is being monitored through your system. What exactly are you measuring, and what can they expect as an outcome from your measuring the tailings condition?
Yeah, so it's a good question. I think it's exactly the same as any other kind of hazard conceptually. The only difference is the inputs are different, and the precise thing you're trying to predict the probability of is slightly different. But in both cases, you're predicting the failure of something. Mm-hmm. So whether it's, again, whether it's a roof fall failure, or it's a rock burst, or it's a pit slope failure, or it's a tailings dam failure of any type, what you need to do is characterize the type of failure you're looking at. And then what we typically do is we have a brainstorming session with people on site, and that may include consultants as well, but people who are knowledgeable about the problem at hand, and look at all of the many variables that people believe may correlate to that hazard. So it could be ground deformation, it could be any kind of monitoring, or anything to do with the properties of the tailings impoundment, the geometry, the rock type, etc. And it could be looking at other variables such as, historical rainfall, or, whatever people think may be correlated to the failure. And then we build a system that can take those different input data sets, compute within the data warehouse the variables of interest, co-locate those variables as described in a data fusion model, and then use those co-located points to combine the variables into a hazard prediction.
Okay, thank you for that answer. Maybe a little bit of the floor for Lenisa to ask a question as well. Go ahead.
Yeah, thank you. Thank you. That was very interesting. What I find that's quite different is that you moved from underground and trying to expand into open pit work. Is that correct? Generally, it's the other way around.
Yeah, that's right. That's correct. We started underground and we have expanded into open pits. We have a few open pit examples that are more recent than the underground work.
That's interesting. So what do you think are the most significant barriers to implementation of your project into mines?
Yeah, so good question. The barriers really come in three types as we found it. One is cost. The cost of the actual technology is not the main cost, though. The real cost is the cost to the site with their internal resources, and that has to do with the availability of people, and it has to do with the state of the data that they have. So we've really worked hard over the last number of years to make sure the system is as automated as possible. So what that means in practice is that at first, of course, you need to do some direct work with the site, but we do most of the work. We need information from them and data samples from them, and then we have to hook up the system to the data sources, and there's some work to do there. But after that upfront work is done, what operations want is a pretty hands-off technology. So they don't want to devote somebody hours a day to your technology. So that's what we learned to be the barrier initially, and that's what we've really worked hard to overcome, to automate things to the greatest degree possible, to make it as light and as easy as possible for the operation to deploy.
Thank you, John. We are running a little bit late on our time for this webinar, but I do want to ask you one other question, and it concerns site-to-site analysis, right? If you have your technology deployed in one site of a mining company, and there's maybe other sites that are within proximity to it, is there a way to correlate the information between the sites?
Yes, absolutely. You can combine data. The data fusion operations can extend from one site to another. And what we have often found is with the hazard models, many of the variables and the relationships do correlate from one site to another. There's a lot of commonality between operations. There's differences, of course, that you have to take into account, but yeah, absolutely, you can accommodate multiple sites into a single system.
Awesome. Thank you for that, John. And John, maybe just to close off, do you have any parting words to say to our ecosystem before we say goodbye?
Well, thanks for listening, and I would love to hear from any of you for whom this presentation of things I've talked about have struck a chord, to see if we can work together. As I said at the beginning, we're looking for pilot project sites, and I would love to get in contact with any of you who may have one to offer to this project.
Okay, thank you very much, John. And folks, there you have it. This is Mira Geoscience with John Magagi sharing with you where his technology is going next. Thank you, John. You have a good day.
Yeah, thank you very much. Bye for now.